today's topic is linear momentum. Here you can see two objects. Object 1 is m1 and object 2 is m2, and their masses are different, but they are having same velocity. Object 1 and object 2, m1 and m2, are having same velocity but different masses. So it's difficult to stop m2. You can stop m1 easily, but for stopping m2 you will require more force. It is because mass of m2 object 2 is greater than mass of object m1, so it's difficult to stop m2. Although both have same velocity, both are moving with same velocity, but it's difficult to stop m2 because it is having greater mass than m1. In another case, you can see that there are two objects m1 and m2, and both are having same masses, but velocity of m1 is greater than velocity of m2. m1 object is moving with greater velocity than m2, but both are having same masses, so it's difficult to stop object m1 because it has greater velocity than m2. So from here we can conclude that for greater masses we need more force to stop, and for greater velocity we need more force to stop that object. So from here we can relate mass and velocity of objects with another physical quantity, and that is known as momentum. The linear momentum represented by P of an object of mass m moving with a velocity v is defined to be the product of the mass and velocity. P is equals to m into v. Product of mass and velocity is linear momentum P. It is a vector quantity, so points in same direction as velocity. So momentum is in the same direction as the direction of velocity. Momentum depends on an object's mass and velocity. It is a vector quantity. Its dimension is equals to m to the power 1, l to the power 1, t to the power minus 1. Its SI unit is kilogram meter per second or Newton into second. Newton's second law and linear momentum. Newton's second law can be used to relate the momentum of an object to the resultant force acting on it. From Newton's second law of motion, F is equals to m into a. Let's say it equation number 1. From definition of acceleration, acceleration is equals to rate of change of velocity, that is final velocity minus initial velocity divided by delta t. Let's say it equation number 2. Putting equation number 2 in equation number 1, we get F is equals to m into Vf minus Vi, final velocity minus initial velocity divided by delta t. Multiplying m with the whole term Vf minus Vi, we get F is equals to m Vf final velocity minus m into Vi initial velocity. Mass into velocity is momentum, so we can write m Vf as Pf, that is final momentum, minus mvi can be written as Pi initial momentum divided by delta t. So Pf minus Pi is change in momentum that can be represented by delta P, and we get force is equals to delta P divided by delta T, that is rate of change of momentum is equals to force The time rate of change of linear momentum of a body is equal to the force acting on the body. Impulse and change of momentum. The impulse represented by J is the product of the force F and the time interval delta t during which the force acts. Mathematically, J is equals to F delta t. The effect of force on an object depends on how large the force is acting and as well as for how long it acts. For a larger force acting for a short period of time, we can have a great effect on the momentum of object. But if we have a smaller force, we can have same effect of momentum on the object by acting this smaller force for a much longer time. J is defined as the impulse. Impulse is a vector quantity. Its direction is the same as the direction of the force. SI unit is kilogram meter per second or Newton second. When the force is not constant, the impulse can be found using the average force. So when force is not constant, we calculate the average force and then we can calculate the impulse by putting this average force. From the relation F is equals to delta P divided by delta T, rate of change of momentum is equal to force. We can put this equation in this equation here and we get J is equals to delta P divided by delta T into delta T, and from here we get J is equals to delta P, that is impulse is equals to change in momentum. Change in momentum is final momentum minus initial momentum, that is mvf minus mvi. When a ball hits with the bat, we get the response of impulse shown by the help of this graph. A large impulse produces a large response. So the ball departs from the bat with a large velocity. If the mass of the ball is less, then it will leave the bat with greater velocity, and if the mass of ball is greater, then it will leave the bat with less velocity. So impulse is related to change in momentum. This line shows the average force and this point is maximum force. Conservation of momentum. In an isolated and closed system, the total momentum of the system remains constant in time. Here we have a system in which there are two objects and there is no external force applied on this system, and this system is having initial momentum and after collision the system is having final momentum. So initial momentum of the system is equal to the final momentum of the system, that is conservation of momentum, and we can prove it from here. We have formula rate of change of momentum is equals to force. As we know that external force is 0 in this isolated system, so we can put F external is equals to 0. So we can write change in momentum as final momentum minus initial momentum, and we get Pf final momentum minus Pi initial momentum is equals to 0 because delta T multiplied by 0 is 0. Any term multiplied by 0 is 0, and we can shift this Pi on second side of the equation and we get final momentum is equals to initial momentum of the system. So from here we know that final momentum of the system must be equals to initial momentum of the system when there is no external force applied on the system. that is known as the conservation of momentum. And the total momentum of the system cannot change when there is no external force applied on the system. This is your class task, try to solve it.